So today we're going to learn about implicit differentiation. And so there's a couple practice exercises. I'd probably do this first part in Desmos just to see what those graphs look like because they are complicated. And the reason they're complicated is because now we have sines and cosines and x's are squared and y's are squared. And so you might want to slip those into Desmos to see what those graphs are going to look like. And then the next thing I would say is this is a really important skill that we're going to learn about today. And so take a few minutes and try and solve for y prime. 6 you can probably do pretty easily, but let's talk about 7. And so when you look at 7 says y prime sine x minus x cosine x equals x y prime plus y. And so in order to solve this, you're going to need to get your y primes together and everything else on the other side. So I'm going to add x cosine x to both sides. And I'm going to subtract xy prime from both sides. So y prime sine x minus xy prime is equal to y plus x cosine x. And so now what you're going to notice is you've got these two y prime terms, and that's going to let you factor those out so that you can isolate that term. So you're going to get y prime, and inside will be sine x minus x equals y plus x cosine x, and now you can isolate the y prime. So you would divide both sides by sine x minus x, divide by sine x minus x, and that will get you what your y prime is equal to. So you've isolated that y prime. And so there's another one of those to try there. You might have to distribute and then gather your y primes and do the same thing that you would there. I've attached the answers to this too. The other thing that is an important skill is to be able to go back and forth between rational powers and radicals. And so in this case, for example, this would be x to the 1/2 times x minus x to the 1/3, and then you would distribute. And so that would get you, when you multiply, you'd get x, and this would then become 1 plus 1/2 minus x times 1/2 times or plus 1/3. And so when you multiply, you add exponents. And so this is going to get you x to the 3/2 minus, this would become x 3/6 plus 2/6 would be to the 5/6. And so you'll see that those distribute like that. If you wanted to put them back inside radicals, this would become a square root of x to the 3rd minus a 6th root x to the 5th. And so that's the kind of thing you would do there. And so those are the kinds of things the skills we might need to do to manipulate things. Like I said, I left the answers for you so you could check on some of your skills. You'll notice they left theirs as radicals rather than putting them back. As rationals rather than putting back at radicals. So what we're going to do today is we're going to talk about how to do implicitly defined functions, what to do with them, making sure we understand how to use chain rules when we do that, finding tangent and normal lines, being able to take higher order derivatives. We're actually going to I don't know if we're going to extend the power rule. We'll have to see what we do. And so an important part in calculus is how to find a slope when the function is not conveniently easy to solve for y. So instead, you just treat y as a variable that you can take the derivative of as a function of x. And when you do that, you would have to take the derivative with respect to x, and therefore you're going to apply what's called the chain rule. And so dy dx becomes part of that. So this is where we kind of switch from that y prime notation and go to the dy dx notation, because we're starting to introduce other variables, and we want to keep track of what we're taking the derivative with respect to. And so by using that chain rule process, we're going to do what's called implicit differentiation. And so the phrase derives from the fact that the equation they're saying here, is that there's explicit formulas to work without being able to solve for just y. You're going to have to find a way to get to it, and you can't isolate a y in that equation, so you're going to have to do it differently. And so here we have that equation. I moved the things around in this slide so that we could talk about it. When you want to apply these, what you do is you differentiate both sides of the equation with respect to x. Then you collect the terms with dy dx on one side of the equation, factor out the dy dx, and then isolate it, just like we did the y prime up above. And so let's try this. So here's a relatively simple one. So the reason it's implicit is because we're applying rules that thus far we've only been able to apply to functions where x was our variable, but now we're applying it to a y. So we have to remember that we're applying a power rule, for example. We're applying a power rule to this side, but we're taking the derivative with respect to x. And so I'm going to rewrite that problem. And so if I were just applying the regular power rule, this would become 2y, but we're not taking the derivative with respect to y, so we're going to go dy dx. And then when you take the derivative of x, it's just 1, but because we're taking the derivative of an x term, we don't need dy dx as part of it. So what we're going to do now is solve for dy dx. And so to do that, we're going to divide both sides by 2y. And so you're going to get the derivative with respect to x is equal to 1 over 2y. And so that's how you would be able to do that derivative implicitly, is we applied the rules that thus far we've only been able to use on x, and we've applied it to the y variable, and then we've used the dy dx as kind of a chain rule to remind us that we're really taking the derivative with respect to x and not y. So we're still finding the slope, the change in y with respect to x, but we're doing it by applying our rules in a new way. So we're just going to keep practicing some of those, and I hope that it'll come together. So that, for example, we're going to find the slope on a circle. And so equations for circles are x squareds plus y squareds when the center's at 0, 0. And this one says the radius is 5, and so it's x squared plus y squared equals r squared. And we want to find the slope at the point 3, negative 4. Well, the slope in our mind is defined as dy dx. So instead of doing all that crazy stuff we've done before, where we're guessing at the slope by picking points nearby, we're going to take the derivative. And so when you're taking the derivative with respect to x, so we're going to go, we're going to take x squared plus y squared equals 25, and we're going to take the derivative of both sides with respect to x. And so when you take the derivative with respect to x, you're going to say, well, the derivative of x squared with respect to x is equal or plus the derivative of y squared with respect to x is equal to the derivative of the constant 25 with respect to x. Well, we can apply these rules on the left-hand side because they're variables. We know what to do. So when we take the derivative of x squared with respect to x, you just get 2x. But we have an issue when we apply that same rule over here, which is we're not taking the derivative with respect to y, we're taking the derivative with respect to x. And so you have to include this extra part right here. And so then when you take the derivative of the right-hand side with respect to x, well, there's no x there, and so it becomes 0. And so in order to finish this derivative, we have to isolate that dy dx term. So we're going to subtract 2x from both sides and get 2y dy dx is equal to negative 2x. Divide both sides by 2y in order to isolate that dy dx term. And then we're going to get negative x over y. And they've asked for the slope of it at a certain point. So you have the point at 3, negative 4. The slope is just negative x over y. And so dy dx is equal to negative 3 over negative 4. So it's just 3/4. And so that's how that's an application of applied implicit differentials. And so we're going to do that same thing again. So example of implicitly defined functions. And so you're going to have to apply that dy dx chain rule again. So like I said, we're going to go d of the function 3y squared plus 2y dx is equal to the derivative of 5x dx. And so we're going to apply that to all of those things. And so we're going to take the derivative of 3y squared with respect to x. We're going to take the derivative, plus the derivative of 2y with respect to x, and we're going to take the derivative of 5x with respect to x. And so when we apply that rule here, we're initially going to apply it just as if it were an x variable, so it's going to become 6y, but then we're going to recognize we're taking the derivative with respect to x, so we have to apply that chain rule type behavior. And then we're going to do that same thing here. The derivative of this component, this component is just 2, but we're applying it to a y and not an x. And so we have to multiply by the derivative of that component itself. And then we're going to take the derivative of this part with respect to x, and so we don't have to do that chain rule part. It just becomes 5. And if you pay attention, now you have 2. Just like we had 2 y primes in the parts in the beginning, we're going to just factor those out. That leaves us this. And so in order to solve for dy dx, you just are going to divide both sides by 6y plus 2. So your derivative with respect to x is this here. And so you got to remember that when you're applying the rules for differentiation and you're taking the derivative with respect to x, that you're going to need to apply a chain rule of dy dx to those y terms that you're using it on. And so I've included the answers that the book printed out to make our lives easier. And so let's try it one more time so that some of your feedback over from the final exam were that you'd like to see examples. And so we're going to take the derivative of 2y with respect to x. We're going to just go ahead and jump right into the derivative of x squared with respect to x, and the derivative of sine y with respect to x, and we're going to apply those derivatives each time. And so you'll notice the first term is a y term, so we're applying that derivative with respect to x. So we're going to have to go, well, it's just 2, but then we have to remember we're applying y dx to it. And then we're going to do that same thing with this. It's just we are taking the derivative with respect to x. So it would actually be dx, which is just 1, so we don't actually have to write it. And then if you don't recall this, I would pull up my cheat sheet at this point and recognize that the derivative of sine y is the cosine of y. But because we're taking the derivative of a y term, you would have to do dy dx. And then you'll notice your dy dx's are on opposite sides. You can go in either direction, it's up to you. So you would go minus cosine y dy dx. If you get the opposite, we're just going to have a negative sign difference in our two answers. So you're going to go 2 dy dx minus cosine y dy dx is equal to 2x. Factor out the dy dx because that's what we're solving for. And then isolate the dy dx. I'm strongly going to encourage you to show all your steps. Don't shortcut your way to the end of this because you'll get lost and confused. So your derivative with respect to x is equal to 2x over 2 minus cosine y. And so that's how you apply take implicit derivatives. And so you apply the rules to y terms, it's just then you use a chain of dy dx. So places you use this are things like lenses and optics and stuff like that. So this talks about in the law that describes how light changes direction as it enters the lens, the important angles are the angles the light make with the line perpendicular to the surface of the lens. So those of you taking physics, you're going to talk about those kind of things. That's called the normal to the surface of the entry. And in a profile view of the lens, the normal is a line perpendicular to that tangent. So you have a curved line, you have the tangent that goes through here, and you have a normal that goes through here. So that's things like your eyeballs or any curved surface. I wear glasses, and so you'll notice they do the same picture here. And so that's the kind of thing. So it says find the tangent and normal to the ellipse at the point -1, 2. And see figure 411. That's the picture that we were just talking about. And so we're going to take the derivative. I'm going to rewrite this. My apologies. X squared minus xy plus y squared equals 7. And we're going to take the derivative explicitly. So we're going to implicitly dx squared dx minus dxy plus dy squared. And these are both with respect to x. Take the derivative of 7 with respect to x as well. So we're taking 4 separate derivatives. We're just going to apply our rules based on what we have. The same rules we've had before apply. So I'm going to analyze this a little bit. This one is going to be a simple derivative. It's just going to be 2x. This one is going to be a product rule because it's two things multiplied. This is going to just be a chain with an implicit, and then the other two are going to be okay. So I'm just wanted to take a minute and look at that. So if I take this derivative with respect to x, it's just 2x. So I'm going to take a second here. F would be x. G would be y. The derivative of x is 1. The derivative of g is dy dx. Because it would technically just be 1 dy dx. So we're going to apply a chain rule to this. So we're going to go the derivative of the first times the second. I'm sorry, that looks like a prime. I'm going to make that go away. Times y plus the derivative of the second times the first. So that's going to become your second term. Y plus dy dx times x plus the second derivative here is 2y dy dx equals 0. Now you still have two instances of the dy dx, so you're going to try and isolate those. Be smart, be careful, there's a negative sign here. So go ahead and distribute that, minus y, minus, I'm going to switch the order of this because I'm weird like that, plus 2y dy dx is equal to 0. And so then I'm going to say, well, I want to isolate these two terms because of this. So I'm going to move the other things to the other side. So I'm going to go minus 2x plus y minus 2x plus y is going to get me negative x dy dx plus 2y dy dx is equal to negative 2x plus y. I'm going to factor that out and get dy dx is equal to negative x plus 2y, negative 2x plus y. I'm going to divide that. Sorry, I put an equal sign. There shouldn't be an equal sign here. It should be a parenthesis. My apologies. Negative x plus 2y, negative x plus 2y. So you're going to get dy dx is equal to negative 2x plus y over negative x plus 2y. So that's your slope. You have the point up there, which is going to give you its normal point right here at negative 1. The slope at its tangent. So it wants find the tangent and normal to the ellipse at that point. So you need the slope of that. So you would say, all right, I'm going to add a page here, sorry. I'm going to go in here and add a page. And so at negative 1, 2, that's not right. Negative 1, 2, I'm going to substitute in. So my slope is equal to negative 2 times negative 1 plus 2 over negative of negative 1 plus 2 times 2 is equal to 2 plus 2 over 1 plus 4. I'm getting 4/5. And so that would be your slope. So if you wanted the equation of the line, y minus y1 is equal to m times x minus x1. So I would get y minus 2 is equal to 4/5 x plus 1. Now, to find a normal to that curve, the equation for the normal, you're going to remember that the m of a perpendicular line is equal to the negative reciprocal of the original line. And so it's going to be, instead of 4/5, your perpendicular slope is negative 5/4. But then the rest of it is the same. So y minus 2 is equal to negative 5/4 x plus 1. And so that is going to be the normal point at that same thing. You can put in Google Classroom, you can put it into Desmos and see that same thing. So here's another example here. A worked out example. Actually, it's a ton of work, and so I decided to do the easier of the two today, and here's those others. So we're going to be working on the examples from this for classwork on Thursday. So I will put the assignment in Google Classroom if you want to get started so that you can get your questions answered during class on Thursday. And then we'll run through some of those together to try and help you out and try and get you to understand what's going on. I hope that helps. I'll be in my office hours, or feel free to email me. Happy New Year. I hope you all had a great break. Thanks.